We're going to talk about the sampling distribution of sample mean and the central limit theorem. I'm going to start off with a couple of formulas that aren't going to mean a whole lot to you at this point. But it says if x bar is the mean of a random sample of size n from an infinite population with mean mu and standard deviation sigma, then mu sub x bar is equal to mu, and sigma x bar is equal to sigma divided by the square root of n. So again, I said that wouldn't mean too much at this point, but what I'm going to do is take a look at an example and kind of go through what this is talking about. So suppose we had this population here. It's normally distributed. The mean is 16. Notice it goes from 0 to 32. And the standard deviation is 5, which means the typical difference from the mean is 5. This is 5 here, 5 here. This represents probably one standard deviation. The middle 68% since it's normally distributed. Okay, so what we're going to do, let's start off with n equals 2 here. I'm going to simulate a random sample of size 2 from this population. So let me do that. I just picked 2. These are the 2 observations that I picked. This is the mean of those 2 observations. Notice it lies almost in the middle of the distribution here, close to the mean. And actually the mean we can see at this point was 17.4. So let's do it again. Get those 2 points. We get a mean here. And now our means slid back down to 15.5 after that second observation, or the second mean. Okay, so we've done it twice now. So let's just do it a couple more times. We get another mean. And we get that. Now, as you can see, this would take a long time because what we're trying to do is say, well, what about all the possible means that we could take from this population? There's an infinite. If we're pulling from an infinite population, there's an infinite number of sample means. Now, usually your population isn't going to be infinite. Any population that we're interested in is going to have a bound, but we usually work with large populations. Okay, so all these numbers are going to be very accurate. Okay, so what I'm going to do is just this says skip 5, do it 5 times. These are 5 more sample means. I can do it 5 more. 5 more. You can start seeing how often these sample means take place. Okay, well, let me just, I did 1,000 more. Notice the total number of means that we've done from this population, or how many times that we've done it, is about 1,048. Notice we can start seeing this thing playing out a little bit. Let me do another 10,000. Once you do 10,000, you're basically looking at what it's going to look like, the true sampling distribution of this. Okay, I can do another. Notice now I'm looking at 21,000 times. I've taken the mean, taken 2 values from this population, taken the mean, and then plotted the mean. Okay, so one thing that we can notice here is the original mean was 16. And the mean of our sampling distribution is 16.05. So let me go back to what we were just saying. That's what this says. The mu by itself is the mean of the population. This is saying that the mean of all of your possible x bars is equal to the mean of your population. Okay. Back to this. Notice you can tell that it's slightly less, has less variation in this distribution. So the standard deviation here is going to be higher than the standard deviation here. We can see that. 5 divided by 3.5. So if you do, go back to this. This is the formula for that. Which means if you take 5, this is the standard deviation of the population. If you divide it by the square root of n, now what n means, little n is your sample size. It's not how many times you've done it or completed the simulation. It's your sample size. So in this case, it's 2. So if you do 5 divided by the square root of 2, you're going to get around 3.5. Okay, so that's what the formulas are talking about. So this is not only true for a normal distribution. We can look at a skewed distribution. Okay, and I'll stick with n equals 2 here. So just do it 2 times. Notice that you're more likely to get values around here now. Notice that the mean of this distribution is 8, which is, let's see, 16's in the middle, 8's around here is the mean. Okay, so we're more likely to get a mean around here. So the first one is pretty much right on it. Doing it again. Okay, and now I'm just going to jump to 10,000 and do that. Okay, and you could see that the mean of the original population is 8.08. The mean of the sampling distributions of all of those means of size 2 is 8.09, pretty much the same value. And 6.22, if you divide that by the square root of 2, again, because we're working on sample size 2, you get the standard deviation. And notice that this has a larger variability than the sampling distribution does. Okay, so we've talked about the mean and standard deviation of the sampling distribution. And remember, when we're describing a distribution, we really wanted to know 3 things. Well, actually 4 things. We wanted to know something about the center, something about spread, something about shape, and then if we have any outliers. So the important 3 are going to be the first 3: center, spread, and shape. So we can kind of talk about shape here. We've already done one example. The normal distribution. The normal distribution, n equals 2. You can see the sample distribution is pretty much normally distributed. And basically any size, sample size, it's going to be normally distributed. Notice again, the center is the same here. U sub x bar, which is the mean of all of the x bars, all of the sample means, is the same as the population. And notice the standard deviation is even smaller here, because when we increase our sample size, the standard deviation gets smaller. But notice that the shape stays the same. It's still normally distributed. And we can go up to n equals 25. Take a look at that. I'll just skip to the 10,000. And you can see what we're working with. The standard deviation pretty small. Mean still the same. And this is actually normally distributed. If you could zoom in on it, it looks a little odd shape just because the standard deviation is pretty small. It's 1. Okay, as opposed to this. But it is normally distributed. Now, one thing we could basically do the remember it's sigma 5 divided by the square root of n, which is the square root of 25. 5 divided by the square root of 25 is 1. So that's our standard deviation there. Okay, so now let's look at a skewed distribution. We've already talked about how the center and spread. We know that those formulas behave. How those formulas behave, we know those from the previous slide. So let's look at shape now. We have, this is the one we just looked at. If you look at this shape, it's not as skewed as this one, but it's still left skewed. If you had to describe this shape, you would call it left skewed. Okay, but if we look at larger values of n equals 5, you could still say that this has got some skew to it to the left, but it's definitely less skewed. Okay, n equals 10. We'll take a look at that. Getting less skewed. Starting to look more like a normal distribution. We still got a skew there, but it's not a bad skew. Okay, and you can see this. That's the normal curve. It's actually starting to fit it pretty good. 16, we'll just look. Still slightly some skew here, but getting better. And as n gets larger, we'll go to n equals 25. As n gets larger, it's going to appear more and more normally distributed. I'm talking about the sampling distribution of the means. Okay, so that brings us to what the central limit theorem is. This is what the central limit theorem says, and this is not basically, this is what the central limit theorem says. As n approaches infinity, which means as sample sizes gets larger and larger and larger, the distribution becomes exactly normal. Okay? So in practice, we know we're never going to have a sample size of infinity. So our distribution is not going to be exactly normal. But we have to come up with some kind of guideline to where we think it's normal enough to use these normal probability formulas and things like that. Well, we already saw it. N equals 25. It was pretty normally distributed, even before that, really. But so a fairly conservative value is n equals 30 or above. So we say if n is greater than or equal to 30, then the sampling distribution of the sample means is approximately normal. Okay. So if you look in another book or another class, they might say 25, they might say 40. It's just a guideline. The central limit theorem just says the bigger n gets, the more normally distributed it is. And remember, that doesn't depend on the shape of the population, because we just looked at a skewed distribution, a right skewed distribution, and as n got larger, the sampling distribution was became normally distributed.